Hi Calculus 1 students. In this video we're going to take a look at some basic rules for differentiation. Let's start out with the simplest rule of all, the constant rule. The constant rule says that if c is a real number, then the derivative of c with respect to x is equal to 0. This ought to make sense. We've seen this before. We said that the rate of change of a constant function was 0 because it was constant, and the derivative is the instantaneous rate of change. Thus, we have the constant rule. Now let's take a look at the power rule. We use the power rule to find derivatives of power functions. Power functions all have the form f of x equals x raised to some power, where the power is a real number. So in this case, it says if n is a non-negative integer, then the derivative of x to the nth power with respect to x is equal to n times x raised to the power and subtract 1. Now, there's one little thing I want you to pay close attention to here. It says if n is a non-negative integer. That part is actually not necessary. As long as n is a real number, the power rule will work. So here are a few examples. Let's suppose we want to take the derivative of x to the 5th power. Then all we have to do is pull down the 5 as the coefficient and make the new exponent 1 less than the old exponent. So the derivative with respect to x of x to the 5th power is 5x to the 4th power. Let's suppose that instead of an integer, we have a fraction, x to the 1/2 power. Remember, x to the 1/2 power is the same as the square root of x. We follow exactly the same rule. We bring down the power as a coefficient, and we subtract 1 off of the exponent. So we have 1/2 times x to the negative 1/2 power. And usually we don't want to leave negatives in exponents, so let's rewrite this as 1 over 2x to the 1/2 power. Let's suppose the exponent is negative, x to the negative 3rd power. We do exactly the same thing. We bring down the exponent to turn it into a coefficient and subtract 1 off of the exponent. So the derivative with respect to x of x to the negative 3rd power is equal to negative 3 times x to the negative 4th power. And rewriting this in simplified form, we had negative 3 over x to the 4th power. And there we go. So that's how the power rule works. Now let's suppose instead of just having a function, we have a constant multiple of a function. So if f is differentiable at x and c is a constant, then the derivative with respect to x of c times f of x is c times the derivative of f. So this is very good when we need to deal with a constant multiple of something. For example, what if we wanted to take the derivative of 5x cubed? This rule takes care of that. It says that this is the same as 5 times the derivative of x cubed. So we see that the constant multiple just comes along for the ride. So we have 5, and then we take the derivative of x cubed. Using our power rule, we see that that's 3x squared. So we now have 15x squared as the derivative of 5x cubed. Now let's suppose we need to deal with a sum or a difference of two functions. Turns out that if f and g are both differentiable at x, then the derivative of f of x plus g of x is the derivative of f of x plus the derivative of g of x. And since we define differences simply to be adding opposites, this also works for subtraction. So we can actually state this rule as the derivative of f of x plus or minus g of x equals the derivative of f plus or minus the derivative of g. So this means that if I want to take the derivative of 5 plus x squared, this rule says that first I should take the derivative of 5, Then I should take the derivative of x squared, and then I should add the results. So I know the derivative of 5 is 0, and I know, whoops, let's erase that extra equal sign there. And then we know that the derivative of x squared is 2x. We add the results together, and we see that the derivative of 5 plus x squared is equal to 2x. So now we know everything we need to know in order to be able to take derivatives of polynomial functions. So see if you can use our new rules to find the derivative of the function g of x equals 6x to the 5th power subtract x. So pause the video, find your derivative, and then restart to check your work. Okay, so let's see how you did. We've got g of x equals 6x to the 5th subtract x. So that means for g prime of x, first I should take the derivative of 6x to the 5th. The 6 is going to come along for the ride, and I find the derivative of x to the 5th using the power rule, which is 5x to the 4th. Now I'm going to subtract the derivative of x, and since x is the same as x to the 1st power, I'll get 1 times x to the 0 power. And cleaning this up, I see that 6 times 5 gives me 30x to the 4th power, and then 1 times x to the 0 power is really just a 1. So the derivative of 6x to the 5th subtract x is 30x to the 4th subtract 1. Now let's take a look at this next example. It says g of r equals the product of 5r cubed plus 3r plus 1 times r squared plus 3. In this particular case, we have a product, and we do not have a rule yet that covers how to deal with derivatives of products. But that's okay because we know how to multiply polynomials. So take a few minutes, multiply out this polynomial, and once you have it expanded out, see if you can take the derivative. So pause the video, work out the problem, and then restart to check your answer. Okay, so let's see how you did. First thing we have to do is some multiplication to figure out what g of r really looks like. So here we go. We're going to multiply out 5r cubed plus 3r plus 1 times r squared plus 3. So we're going to have 5r to the 5th power, right here, plus 3r to the 3rd power, plus r squared, plus 15r cubed, plus 9r, plus 3. And then combining our like terms, we have one copy, 5r to the 5th power. For cubes, we see that there are a couple of cube terms, so we're going to add those together to get 18r cubed. And then we have, let's see, one copy of r squared, one copy of 9r, and then a single constant, which is 3. So now we have g of r. Once we've got g of r written out in standard polynomial form, we can take the derivative. So g prime of r will be equal to 25 r to the 4th power, constant multiple rule and power rule, plus, now we're going to multiply 3 times 18. So that's going to be 54 r squared. R squared turns into twice r, 9r turns into 9, and 3 becomes 0, and we don't bother to write the 0 down. So g prime of r is 25r to the 4th power plus 54r squared plus 2r plus 9. So here are some functions that are similar to polynomial functions, but they're not quite polynomials because we have some exponents that are not non-negative integers. So take a few minutes and see if you can find the derivatives for s of t and h of x. Pause the video, work out the problems, and then restart to check your work. Okay, so let's see how things went. So for s of t, it's a good idea to rewrite that square root as t to the 1/2 power instead of the square root of t. So that's the one change I'm going to make. to the way I'm writing my function before I actually take my derivative. So I'm going to write 4t to the 1/2 power minus 1/4 t to the 4th plus t plus 1. So that means I can now find s prime of t using my rules. So 4 times 1/2 is 2, and then 1/2 minus 1/2 is negative 1/2. So the derivative of 4t to the 1/2 power is 2t to the negative 1/2 power. Now I'm going to put minus 4 times 1/4 is 1, and 4 minus 1 is 3. So my second derivative is t cubed. T becomes 1, and 1 becomes 0. And since I have that minus 1/2 power in there, I'm going to clean up just a little and write this in simplified form. S prime of t equals 2 over the square root of t minus t cubed plus 1. It's also perfectly appropriate to write 2 over t to the 1/2 power. Either one is okay. For the second problem, h of x equals the root of x times the root of x minus 1, I'm going to go ahead and multiply this out. So that'll give me x minus x to the 1/2 power. And now I can take the derivative. So h prime of x equals 1 minus 1/2 x to the minus 1/2 power. And again, since we don't want to leave a negative in the exponent, I'm going to rewrite this as 1 subtract 1 over 2 times the square root of x. So now that we know how to handle polynomials, what about rational functions? Since rational functions are quotients of polynomials. It turns out that some rational functions we need a special rule to deal with. But if we can reduce our rational function so that there is no longer a denominator present, then we will be able to use the rules we already know. So let's take a look at this function h of x equals x cubed minus 6x squared plus 8x divided by x squared minus 2x. What I'm going to do is I'm going to factor the numerator and denominator of this function to see whether or not I can reduce. So taking a look at the numerator, I see that there is a GCF. And that GCF is x. So I'm going to pull x out, and that leaves me with x squared minus 6x plus 8. And I see that there's a GCF of x in the denominator as well. So that's x times x minus 2. So already I can see that I can cancel out a factor of x. Now I'm going to keep factoring in the numerator. X squared minus 6x plus 8, I want to factor as well. So I say, all right, well, 8 is 4 times 2, so that's x minus 4 times x minus 2 divided by x minus 2. So I see again, I can cancel out from the numerator and denominator the factor of x minus 2, and it turns out that h of x can reduce down to x subtract 4. Now remember earlier, we saw that we didn't have any trouble if we were looking at a location where there might be a hole in a graph. So notice what we've done is we've just cleared out all of the holes in our graphs. So now when we go in and take our derivative, we'll take the derivative of x subtract 4, which is simply 1. So what this tells us is that wherever h of x is defined, its derivative will be equal to 1. So it has a derivative of 1 everywhere except where x equals 0 and x equals 2, where our function isn't defined. So with that in mind, see if you can find the derivative for y equals x squared minus 2ax plus a squared divided by x minus a, where a is a constant. So pause the video, work out the problem, and then restart to check your answer. So let's see how you did. First thing we want to do is reduce this function. So notice that the numerator is going to be the square of the binomial x minus a. That means we can rewrite that function as simply y equals x subtract a. Now we can go in and take our derivative. Using the power rule, x turns into 1, and using the constant rule, a turns into 0. So we end up with the derivative y prime equals 1. Now let's take a look at one more kind of function. And this is the natural exponential function, f of x equals e to the x power. This function shows up all over the place, and it's so common that we're going to go ahead and talk about its derivative. And it turns out that the natural exponential function is special because it is the one function which is its own derivative. The derivative of e to the x is equal to e to the x. So now that we know a little bit about derivatives, let's talk about higher order derivatives. It turns out that all the derivatives we've looked at so far are what are termed first order derivatives, or simply first derivatives. So the order is which derivative you're looking at. When you take the derivative of a function, you end up with another function, and that function has its own derivative, and that derivative has its own derivative, and so on. So we end up with higher order derivatives. So let's suppose we start out with a simple function. F of x is equal to 5x cubed minus 2x squared plus 4x minus 6. And I want to take some derivatives of this function. I'm going to start out by using prime notation. So my first derivative, f prime of x, I simply use my new rules. So I end up with 15x squared minus 4x plus 4. Now I'm going to take the second derivative. In order to indicate a second derivative, I put two prime symbols. This is read f double prime of x, or the second derivative of f with respect to x. Now I take the derivative again. 2 times 15 is 30, x minus 4. Now I'm going to take the derivative of the second derivative, which is called the third derivative. So now I put 3 little prime symbols. So the third derivative, or f triple prime of x. So I take the derivative of 30x and I get 30, and I take the derivative of 4 and I get 0. So now I'll take the next derivative. That'll be the fourth derivative. Once we get past 3 tick marks, instead of using tick marks, we start putting the order of the derivative in parentheses as a superscript. So if I see f with a superscript of 4 in parentheses of x, that says that I'm looking at the fourth derivative of the function f. Well, since 30 is a constant, its derivative is 0. So that means all the other derivatives down the road are going to end up being 0. So the fifth derivative, well, the derivative of 0 is still 0, and so on. So that's a higher order derivative, a derivative of a derivative. Now let's look and see what happens if we look at the higher order derivatives of e to the x power. So f of x equals e to the x power. So now I'm going to go and I'm going to use Leibniz's notation. So y equals e to the x is my starting function. So the first derivative is dy dx equals e to the x power, because the natural exponential function is its own derivative. Now I'm going to take the second derivative. To indicate the second derivative, you put a superscript on the d in the numerator of the notation, and a superscript of 2 on the input variable in the bottom. So that's the second derivative of y with respect to x. And well, that's still e to the x. If I want the third derivative, I change my superscripts to a 3, and the derivative of e to the x is e to the x. So notice it doesn't matter how far I go in the list, all of the derivatives of e to the x are always e to the x power. Now let's take a look at f of x equals 3x to the negative 2 power, and let's use operator notation. So if I want to take the first derivative of 3x to the negative 2 power, that'll be negative 6 x to the negative 3rd power. To indicate that I'm going to take a second derivative, I put a superscript of 2 on my derivative operator. So now I'm going to take the second derivative of 3x to the negative 2, which is equal to the first derivative of negative 6x to the negative third power, which is equal to 18x to the negative fourth power. To get the third derivative, I put a superscript of 3 on my notation. The third derivative of 3x to the negative 2 is the derivative of 18x to the negative 4. So now I'm going to multiply the negative 4 and the 18 together and get negative 72x to the negative fifth. If I want the fourth derivative, my superscript becomes a 4. And so now I'm going to take the derivative of negative 72 x to the negative fifth power. So I take negative 5 and negative 72 and multiply them together and end up with 360 x to the negative sixth power. So notice the pattern here. I started off with 3x to the negative 2, and because the exponent was negative, my first derivative has a negative on it. But then when I take the second derivative, my coefficient becomes positive again because I'm multiplying two negatives. The third derivative is negative, the fourth derivative is positive, the fifth derivative will be back to having a negative coefficient again. So with these negative exponents, I end up with my derivatives having alternating signs. Now let's look at an example where we use Newton's notation, and this will make it pretty clear why we don't use Newton's notation much these days. So let's suppose we have y equals 6 times x squared. We put a dot over the y to indicate we're going to take the first derivative, which will be 12x. We put 2 dots over the y to indicate the second derivative. We put 3 dots to indicate we're taking the third derivative. We put 4 dots to indicate we have the fourth derivative. 5 dots for the fifth derivative, and so on. So these little stacks of dots get pretty ugly and pretty hard to read pretty quickly. So that's why Newton's notation is pretty much not used anymore, except in, occasionally rare instances. I have seen it a few times in physics books, but that's about it. So now let's actually do something with these derivatives. We're going to find some equations for tangent lines. So in this particular case, we're given a function and we're asked to find an equation of the tangent line to the given curve at A. So remember what the first derivative is. It's a formula for finding the slope of the tangent line. So in order to answer this question, we need to know two things. We need to know a slope and we need to know a point. And if we know a slope and a point, we can write the equation of the line. So let's start out with the slope. I need a formula to calculate it, so I'm going to find the derivative of my function. So I know e to the x is its own derivative, so e to the x over 4 is still e to the x over 4, and minus x becomes minus 1. That's a formula for finding the slope. To get the actual slope, I need to plug in the x-coordinate of the point where I'm going to draw my line. So it said the x-coordinate of the point where I'm going to draw my line is 0. So I'm going to plug 0 in for x. E to the 0 over 4 minus 1 is equal to 1/4 minus 1, and that is negative 3/4. So I now have my slope. Now I need a point. So to get my point, I've already got an input coordinate, 0. I need an output coordinate. So I'm going to plug 0 in for x in my original function. So e to the 0 over 4 minus 0 equals 1/4. So that means that my ordered pair where I'm drawing the tangent line has the coordinate 0, 1/4. So I now have a point and a slope. I can write the equation of my line in point-slope form. So I have y minus the y-coordinate of my point equals the slope times x minus the x-coordinate of my ordered pair. And that is the equation of my line, and I'm all finished. If you like, you can go ahead and write this in slope-intercept form. Y equals -3/4 times x plus 1/4. But that's not necessary. Most of the time, we're going to be perfectly happy at this stage with the point-slope form. So now let's expand that idea and see if we can write the equation of a normal line. A normal line is a line that's perpendicular to your tangent line. So what you need to know is the relationship between the slopes of two lines that are perpendicular. Remember that perpendicular lines have opposite reciprocal slopes. So here's the breakdown of what you need in order to solve this problem. You need a point that's on your line, which you are already given. The point where you're going to draw your normal line is 4, 2. Then you need to know the slope of the normal line. What you can calculate directly is the slope of the tangent line, which is perpendicular to the line you want. So use that information to find your slope, and then take your point and your slope and plug it into point-slope formula. So pause the video, see if you can work out the problem, and then restart to see how you did. Okay, so let's check your work. So first thing I need to do is find the derivative of my function. Since y equals the square root of x, y prime will be 1/2 times x to the -1/2 power. So to get my slope, I need to plug 4 in for x. So 1/2 times 4 to the -1/2 power, or 1/2 times 1 over the square root of 4. The square root of 4 is 2, so that's 1/4. So now I have my slope and I have my point. I can write the equation of the normal line. So the slope for a line perpendicular to my tangent line is -4. So y subtract 2 equals -4 times x subtract 4 is the equation of my normal line. Let's try one more application problem. In this case, we're actually going to aim a tangent line. It says, given the function f and a point q, find all the points p on the graph of f so that the tangent line to f at p passes through the point q. Check your work by graphing f and the tangent lines. So it says f of x should be equal to e to the minus x power, and q should be equal to 1, -4. So here we go. Point P is going to be a point on the graph of f, and we want the tangent line to f at P to pass through Q. So let's suppose that our point P has coordinates a, b. That means that when we look at Q, Q is also on the same line as point P. So here we go. First, let's find the derivative. So f prime of x equals. Now, this one has a little trick in it. It says e to the -x power. There's a little bit of something we don't know about yet trapped inside of this problem, but I'll tell you how to deal with this. Anytime you have a multiple of x up there in the exponent, all you have to do to finish your derivative is to multiply by whatever that coefficient is on the x up there in the exponent. So it turns out the derivative of e to the minus x is minus e to the minus x power. So now I have my derivative. That is my slope formula. Now let's take a look at this. So I'm going to go in here and I'm going to write down the equation of my tangent line. So I have y minus the y coordinate of the point on my line. Well, that's e to the minus x power. Equals our slope, which is minus e to the minus x power, times x minus the x coordinate of our point. Now here I see I have a problem. I've got too many x's floating around in here. I've got x and x. So that looks like it's going to zero out. That's why I want to do this little trick where I put in some placeholder variable. So let's back up and clean this up just a little bit. So if I'm looking at point P, f of a is equal to e to the minus a power. So we'll have going in here y minus e to the minus a equals our slope, which will be minus e to the minus a, times x subtract a, like so. So now we have a formula written all in terms of the input of our point. Now, taking a look at this line, we know that point Q has to live on this line. So let's go ahead and plug in the values from point Q for x and y. So that means y will now be negative 4. We have minus e to the minus a equals minus e to the minus a. And now x is going to be 1. So we'll have 1 minus a in the parentheses. And now let's go in here and play cleanup. So we've got minus 4 equals minus e to the minus a plus a e to the minus a plus e to the minus a, for moving this minus e to the minus a to the other side of the equation. Notice minus e to the minus a and plus e to the minus a cancel out, leaving us with negative 4 equals a e to the minus a power. Now all we have to do to find all our points P is solve that equation for a. So here we go. Let's solve this equation. First thing we need to do is divide everything by a. That'll get the exponential piece by itself. Then, to get the a out of the exponent in the natural exponential function, we should take the log of both sides, like so. But now we see that we have a problem. We have the a trapped both inside the logarithm and outside the logarithm. Just like before, we had a trapped outside of the exponential function and inside the exponential function, which is just a little bit tricky. Here's what you can do to get around that problem. Notice that inside this logarithm we have minus 4 divided by a. Logarithms only can be applied to non-negative numbers. So that means minus 4 over a has to be positive. That tells us that a has to be smaller than 0. Now, this outcome over here is therefore a positive number. Minus a is positive if a is less than 0. Those two pieces of information together will allow us to set up a window in our graphing calculator. So what you want to do is let y1 be the natural log of negative 4 divided by x, and let y2 be equal to the opposite of x. Graph those together and find their intersection point, and that will give you the x-coordinate of the point you're looking for. When you graph those two functions in your calculator, you should see something that looks very similar to what I've drawn on my page here. And going in and using the intersect feature, you can find the values at this intersection point. And what you will see is that the x part of that is approximately equal to negative 1.202168. And that's what we're really looking for. That's the x-coordinate of the point that we're trying to find. Now, let's go back and see what our original function looked like. Our original function was f of x equals e to the minus x power. So that means that in order to find our y-coordinate, we need to find e raised to the power 1.202168. So plugging that into our formula, we see that f we see that f of negative 1.202168 is approximately equal to 3.3273. So now we know about where our ordered pair lives. Our ordered pair has approximate coordinates of negative 1.202, comma, 3.327. And that is how you aim a tangent line. So there are a few basic applications of what we can do with derivatives.